In this video, we will be discussing the use of exploratory for explanatory analytics. Explanatory analytics are employed when one has a hypothesis or something that they would like to test in their dataset. To perform explanatory analytics, one needs to first make sure that the dataset is in a form that is suitable for such analytics. This requires that the data be expressed in multi-row, multi-column form, where each column represents a separate variable or separate fact about the data. Consequently, data wrangling for explanatory analytics requires that the data be in long form versus wide form. Hypothesis testing is known more commonly as regression analysis, and there are a variety of regressions that one can run on data. In this video, we will take a look at a very simple, generalized linear model to analyze data. Topics we will cover will include specifying the model, visualizing the explanation that the model is giving us, and checking to make sure that the model is correct. In this walkthrough, the data is going to be based on the Mannheim case, and information at the Mannheim case is present at that link. This case is about an auto dealership that has cars that it sells either through auction or online. And so it is used car sales data. The data set is known as Mannheim.csv, and we will be visualizing different aspects about the data and consequently building a model based on this data. The subsequent slides in the exploratory slide deck related to explanatory analytics walk through the different aspects of the analysis, such as visualizing scatter plots before the analysis, building of the model, and graphing of the residuals after the analysis. Let's get started with analyzing this data in Exploratory. As we can see here, a new exploratory project has been created with the name as follows: demo_explanatory analytics. In this project, there is no data set, and we will be importing a data set as follows. Clicking on the plus sign right next to data frames, we will be bringing in file data. This file data is stored on a remote server and is going to be in a text file. The remote file URL that we're going to be using is present in the link to files document that has been uploaded to the website. Once you put the link to the remote file into the remote file URL, you can click on OK, and the data is fetched, and we can see that this data is structured appropriately. We see the names of the columns: model, price, miles, and sale, and we see that we have a variety of rows and 4 columns. We don't need to modify anything in the importation of data, and so we can click Save and give our data frame a name, in this case Mannheim. We see that we have 4 attributes or 4 columns in our data: model, and this seems to be model X, Y, and Z. Since this is used car sales, we can assume this is X model cars, Y model cars, and Z model cars. We see price, that has a minimum of 4,500 and a maximum of 35,400. Obviously, price is expressed in dollars. We see the mileage of the cars, and we see sale, or the type of sale, which is at auction or online. Subsequently, our raw data looks like this, where we have the model, the price, the miles, and the sale of the car, and how the car was sold. If one wants to build a model based on this data, one would expect that the price of the car is dependent on a variety of different characteristics. For instance, the price of the car can be determined by miles. Since it's a used car, the more miles on the car, the lower the price of the car. And consequently, we can assume or we can infer that as miles of a car increase, the price of the car goes down. We can also say something about model. Different models of cars have different prices. We don't know how X, Y, and Z are structured, but we can assume that we can infer that there might be some association between the price and the model of the car. We're not exactly certain whether the price of the car is going to be influenced by how a car was sold, but we have that data here as well. To see whether there are any patterns in the data that'll help us build a model, one of the things that we can do is we can start visualizing the data and the relationship between um, different columns in our data, and we can do that by using charts. So we can click on a chart, and we can start off by building these things known as scatter plots. And in this case, one of the things that I'm interested in is understanding is how the price of the car is related to certain factors, other facts about the car. And so on the x-axis, I can say, I want to see how miles is related to the price of the car. And by just plotting out miles versus the price of the car, where miles is on the x-axis and the price of the car is on the y-axis, we see that the greater the number of miles on the car, we see a decrease in prices. Right? Now, we see three bands over here, supposedly three bands, and one of the things that we can do is we can decide to color these dots by one of the other aspects about the data. And since we have three models, if we color by the model of the car, we see that each model has a range of prices that it is sold at. If X, being the blue model, blue dots, suggests that X is the base model maybe, and Z is the top end model. And so each of these models of cars has an association between price and miles. As the miles go up, the price of the car decreases. I should be giving this chart a title. This is a chart of price versus miles based on the model of the car. And so this gives us some idea about the relationship between different columns in our data. We also have another column known as sale, or how the car was sold. So we can build another chart. Again, I shall be using a scatter plot. Again, the x-axis is going to be miles. The y-axis is going to be price. But instead of coloring by the model of the car, I shall be coloring by how the car was sold. We still see the three bands, but we see something else. We see that the orange dots being when cars were sold online, tend to be for low mileage cars. And low mileage being low miles than around 40,000 miles. Under 40,000 miles, we see there are quite a few cars that are sold online of the X model, some of the Y, and a few of the Z. Above 40,000 miles, however, there aren't as many cars sold online. And so this gives us another sense about the relationship between how a car is sold and a possible association with price or miles. Again, I shall give this chart a title. Based on these visualizations, we can confidently say that the price of the car is in fact dependent on miles of the car, the model of the car, and there is some association of the way the car is sold. And so this data uh, says something about the association between the variables. In our case, the variables are model, price, miles, and sale. When we look at these variables, we have to first decide which is the variable that we're going to try to explain. Our models always seek to explain something. In this case, we are trying to explain the variation in price. How does the price of a used car vary? And how much does miles, model, and sale affect the price of a used car? Consequently, price in this case is our dependent variable, or it depends on a combination of other independent variables. The independent variables in our case are miles, how many miles are on the car, model, what is the model of the car, and sale, how a car was sold. These three variables are hypothesized to influence the price at which a car is sold. To test this out, we will need to build a model, and we're going to be using a GLM model. Before we move to model building, first, let's make sure our data is in the right form for analysis. We have one column that contains the dependent variable, and we have three columns that contain the independent variables. It doesn't seem like any of these columns has problematic data, has null data that needs to be accounted for. There are 819 rows, so if I look at 500 rows, I can see that the data looks good. Even the summary tables tell me that there are no missing values in the data. NAs tend to be zeros. So this data seems to be in a form that's already suitable for analysis. And so, to build a model, we shall first add a new step. To run analytics, we need to add a new step. And the step we want to select for regression analytics is to build and evaluate a model. The model that we're going to build is a GLM, or a generalized linear model. So let's click on GLM, and we see the following window. We have to build a GLM model where we have predictors, or our independent variables, and the thing that we want to predict, or our dependent variable. The thing that we want to predict in our case is the price of the car. And we want to say that the price of a car is dependent on the miles, the model, and how a car was sold. Now, one of the things that we can do is we can split this data into training sets and test data sets. What that does is it takes the entire data set and splits it up. The reason we might want to do this is we might want to build our model on a training data set and then test the efficacy of a model on a test data set and see how much of the test data set does our model explain. In our case, for this example, we are not going to split the data set. We're going to leave this as it is, and we can, if we have missing values, decide how we want to treat missing values. We might want to treat missing values as null. We might want to exclude them. We might want to perform different types of things to missing values. Right? In our case, we have no missing values. And if we do have missing values, we'll just leave the default in place. Once we have this model, the different components of the model selected, we can run it. And once the model is run, this is what we shall see on screen. We see a summary of statistics related to the model. Now, a couple of things about this model. As with any regression-based analysis, we have some estimates about the model. These estimates tell us about how good our variables, our independent variables, are at explaining the variation or the variance in price or in the dependent variable. In this case, our independent variables were miles, model, and sale. And this model is going to tell us how effective these independent variables are in explaining our dependent variable, which is the price of a car. To do that, we have to take a look at the parameter estimates and a couple of specific columns within the parameter estimates. The first column that we want to pay attention to is the p-value. The p-value tells us whether any of our independent variables have a significant effect on the dependent variable. A significant effect is an effect that we are certain about that is likely to happen beyond just random chance. In this case, we are looking for p-values less than 0.05. P-values, to be significant for an independent variable, need to be less than 0.05. We notice that these values over here are 0. In fact, they're quite significant, and so we can say something to the effect that all of the independent variables in our case have a significant effect on the dependent variable. In addition to the independent variables, we also have an intercept value. The intercept value is the value that the best fitting line makes as it intersects the y-axis. If all of the independent variables are assumed to have no effect, the line of least fit has an intercept or has an intersection with the y-axis. That line that intersects the y-axis has a certain number, and that is what the intercept is. Now, once we see that our p-values are significant, the next thing we're going to pay attention to is we're going to pay attention to the size of the effects for each of these variables. First note that the intercept value is 22,887.74. The intercept value of 22,887.74 is the mean value of the y-axis when all the independent variables, miles, model, and sale, are 0. Next, the coefficient of miles, again, given that the p-value is significant, tells us that for each additional mile, the price of the car goes down by 0.13 or 13 cents. For each additional mile of the car, the price of the car goes down by 13 cents. Model and sale have to be interpreted slightly differently. The reason that model and sale have to be interpreted differently from miles is because miles was continuous data. Miles is data that is numerical, and it is continuous in the sense that 2 miles is 1 more than 1 mile, and 6 miles is thrice of 2 miles, and so subsequently each additional mile is 1 more unit compared to the previous value. And so one can interpret the coefficient of miles because miles and price are both continuous variables. And so each additional mile has a negative effect on price or drives down price because of the negative sign by 0.13, which is 13 cents. Model, however, is different. Model is text data, it is string data, or it can be considered to be categorical data, right? Model X, Model Y, and Model Z are 3 different types of cars. And what the coefficient of these variables tell you is how the price of Model Z and Model Y cars differ, right? But they have to differ from some sort of base value. In our case, the base value of model is x. So there is a base level of x that is assumed, and compared to x model cars, Z model cars bring in $12,240 on average versus Y model cars that bring in $5,616 on average. Again, model is a significant variable, and so Model Y and Model Z cars are significantly different from Model X cars and bring in subsequently more money than Model X cars. Similarly, sale is also string data or categorical data, and the base level of sale in our case in this analysis is auction. Compared to cars sold at auction, sales online are significantly different and bring in $591.75. This is how one would go ahead and interpret the results of a regression analysis. And so the hypothesis that miles, model, and sale significantly influence the price of a car is true. Model, miles, and sale online are all three highly influential in the price at which a car is sold. The next question one might ask is, well, how much more of a price of a car uh, needs to be explained? Do these three independent variables, miles, model, and sale, uh, explain enough of the variation of the price of a car? One can look at the effects of this model in explaining the data doing the following. One can add a new step, and in this step, one can take the model and predict it. One can see the effect of this model on explaining the data once again. We built this model from our training data, and we can take this model and apply it on the training data and see how well this model does in explaining the variation in price. Subsequently, when I predict on training data, I can run this. Notice that I still have 819 rows. These are my initial observations. I had 819 rows of data with model, price, miles, and sale. Notice that I have some more columns now. In this case, one of the columns that I'm interested in is predicted value. Predicted value takes the coefficients, which is the coefficient for miles, the coefficient for sale, the coefficient for model, and uses those to calculate the predicted value of the price of a car based on the model. The actual price of the car that was sold was $23,200. The predicted value based on the model is $23,236. The next column we want to pay attention to is residual right here. Residual tells us how much our model varies from the actual observed value. And so we are $36 above in the predicted value, and so the residual is minus 36 because the actual price was $23,200. And subsequently, this table contains values of predicted values based on the model and the residuals based on the difference between predicted and the actual price of the car. Note that the price of the car is determined by this equation where we had the intercept, we had the coefficient of miles, and we had coefficients for model type and sale type. We can use the residuals and the actual price of the car to determine how well our model does in explaining the actual price of the car. So we can build a chart, and I shall be building a new chart. Again, notice that this new chart is pinned to the results of our prediction, or the prediction based on the training data, and we will be building a scatter plot. Our x-axis is going to be price, and our y-axis in this case is going to be residuals. Now, a couple of things to notice about this. What I am trying to do by looking at a scatter plot of price versus residuals is to look at how the residuals are distributed. If the residuals, that is what is left after accounting for variations in price based on miles, model, and how a car was sold, right? And so the residuals refers to the unexplained component in the price, right? The stuff that is left over after our model has accounted for these three different things. If residuals are randomly distributed across this XY space, then we can say that the residuals represent noisiness in the data. It refers to just the fact that there is unexplained components everywhere. It refers to noise, and there is no pattern in the residuals, and so our model sufficiently explains most of the variation in the data, right? Now, we need to look at this picture and determine if the residuals are randomly distributed. Before we do that, notice that we have one point right here where we have a residual of minus 13,809. And so this seems to be an outlier, so I shall be excluding it from the analysis by clicking on the point and clicking on exclude. And so I can see kind of a closer view of the residuals. Now, if I color these residuals by, for instance, the model of the car, we see that each model has a separate band. Each model has a separate cluster. And these clusters tend to be a little bit more random for X model cars, but seem to have a definite pattern for Z and Y model cars. For Z model cars, that is the yellow points, we can see that the residuals have a slight slope to them. Similarly for Y model cars. For X model cars, it's a little bit more random, but again, there might be a pattern, right? The purpose of a residuals analysis is to look at the residuals and determine if there are potentially more variables to include in the analysis to better explain your dependent variable. In our case, it seems that there is some more explaining we can do. We don't have the variables about the car, in this case about the way a car was sold, or other data about the people buying the car that can maybe explain the variation in price. But there still seems to be a little bit more that can be explained based on this look at the residuals. One can also color by the way a car was sold to see if there is any effect of the way a car was sold, and does that tell us anything as well about how much is there to be explained based on the way a car was sold and the price of the car. This concludes the discussion of explanatory analytics using exploratory. Thank you very much. Let me know if there are any questions.